Hello, this is ee542 Fall 2025 lab 3 AWS tutorial and fast reliable TCP transfer using TCP stack modification. This presented by me, Syed Aqib Haider, and my teammates Kailin Cho and Ravi Kothari. Now, let's get started. So, part 1, using AWS instances tutorial. So I will show you the instances that we have been using. As you can see, I have installed a lot of instances. However, for the presentation, this is basically we had some issues or the other while installation of the AWS EC2 instances. And finally, we'll have these three as our machines: C13, R11 is our router, C13 is our client, and S15 is our server. So let us go through their topology. Let's connect to the server. Okay. So as we can see, there are this ENS5 is the standard network interface. This is for public internet, and this ENS6 is our IP address for the client. This is basically C13, the client, and our client subnet is 10.0.1, and our client IP is 10.0.1.177. Let us see the routes that we have set up statically. So we can see that this third line 10.0.2.0/24, this is the server subnet, and we have set up statically to go it through the router has this 10.0.1.36 IP in the server subnet. Now let's go to our server. These are various interfaces through which you can connect. Right now we are just connecting through EC2 serial console. For this connection, make sure you have set a password for your machine. This requires a password for your account. So basically, once you launch a VM, you should connect through EC2 instance or SSH client, and then immediately set up a password, because sometimes EC2 instant connect doesn't work, SSH doesn't work. Sometimes you lose IP address, or some issues may happen. We experienced that a lot during the lab. Okay, so here we see. So this is the server client interfaces. Like before, this is the main interface that connects to the internet. This is not our priority right now. This is our internet, not internet, our local subnet. This is our basically server subnet 10.0.2.0/24, and the server has this IP 2.136, and we can see IP route. So this 10.0.1.0/24, it goes through 2.94. This is the router IP in the server subnet. Now let's check the router once. Router is R11 in our setup. Oh, so it's asking for the password, like I said. Ubuntu password. Oh, it's showing incorrect. I guess I should just connect through the IP. Sometimes it shows incorrect. Let me just update the password. Sudo password Ubuntu. Okay, password unchanged. Then why is it not? Something's wrong with this. So let us just stay here in the EC2 connect. IP ADDR show. Okay, so this is ENS5 is for the public internet, and ENS6 and ENS7 are two interfaces, one in server and one in client subnet. We can see 10.0.2.94, this is in the server subnet, and 10.1.36, this is in the client subnet. So this is our basic topology. For setting up this, we had to create instances like network interfaces. You can see there are a lot of interfaces, out of which some of them are relevant to our machines, some are for previous instances that I might have created in the process. But if we want to see which interfaces are connected, we can see from the machines itself. Like this is C13, our client. We can go to networking. This is our VPC for this lab. This is the subnet IP. Basically, CINET is for client internet. These are the two interfaces. This is for the public internet. This is our relevant internet. That is the subnet for the topology, relevant topology, and we can see it has this IP like we saw in the terminal interface also. Similarly, we can have a quick look at the router as well as the server, then we'll move forward to the demonstration of TCP performance. Okay, so this is R11, the same subnet, lab3 part 3. We can also see the MAC address on there. Anyways, this is the main interface for the internet. It has this public IP using which we connect through EC2 Instance Connect. This is the client side interface with this IP 10.0.1.36. This is server side router IP 10.0.2.94. Let's have a quick look at server. See, same VPC, SINET server. INET is for server public internet. Okay, so these are the two interfaces. This is for the internet. This is its public IP, and this is its ENI for the server subnet for our network topology, with this 10.0.2.136 as the IP for the server. Okay, so we can also have a quick look at the topology subnets created. See, this is the lab3 part 3. This is our relevant VPC. These are our subnets, mainly client subnet and server subnet, with these CIDRs 10.0.1.0/24, 10.0.2.0/24. Now this was basically the AWS tutorial. Now we will skip the part 2 and part 4, that is just repetition of lab2 code on our AWS setup, because that is just presented in the report, and that is relatively straightforward. And if we are able to demonstrate part 3, we can also, it is very much straightforward to implement part 2 and part 3. So this part we are not demonstrating because it is present in the report, but it's pretty straightforward. And we will demonstrate this part 3, and part 4 also. We'll just have to repeat step 2 of this experiment, basically lab 2 code under the modified stack. So we'll skip that also, but we'll demonstrate this part, modifying TCP module. So for that, the initial experiment also have been done and presented in the report. So we start with improving TCP performance. So for that, we need to build an Ubuntu kernel. So we have already done that in our instances, not the router but the server and the client. So we can just check grep menu entry, should be boot grep dot config grep menu entry. So as we can see, there are this version 6.17.0 RC5 plus. This is our custom kernel version, and 4.4.0.1128 AWS. This is our main version in which these instances were launched. And currently we are in the custom kernel version, uname r. So we can see 6.1.17.0. Okay, so let us now quickly go to the code that we have modified. We have modified some files in it, tcp.c. These were basically present in the TCP stack. Let me just show you in the kernel. It has a parallel such stack in the client itself. We will demonstrate it in one machine, let's say server for now. So as we can see, we have this Linux vanilla in which our source custom Ubuntu kernel is present. So we do cd Linux vanilla net IPv4 ls. So we can see there are a lot of files, including TCP files. Out of these files, the relevant files were these, which I downloaded from the VMs to S3 and S3 bucket, and from there to my own PC to modify it. So I'll quickly look at these. So first we'll have a look at tcp.h. Okay, so as we can see, these are some changes we have made. First is max TCP window, we have increased its size to 64 kilobytes. And secondly, fast retransmission threshold. It's basically replacing the concept of 3 acknowledgements with 1. So this is like in original TCP we have 3 acknowledgements, but in this case we have reduced it to 1 so as to uh, speed up the TCP transfer. These are retries before a connection is um, you know how many retries are made for making a connection. That was 6, now it is 5. We have changed it to 5. Now this is according to the lab. Original was max RTO into 1 second, so we have reduced this TCP RTO max. We have also reduced TCP RTO min to hertz divided by 10, and initial TCP timeout we have reduced from 1 hertz to hertz by 5. Hertz edge set is basically a OS specific number that is usually 250. Here we have increased the window scaling from 3 to 6 to increase the congestion window size, and we have turned on the Nagel algorithm, basically turned off the off flag for Nagel. TCP initial congestion window, it was originally 10, we have made it 1000. Okay. And here we have set the RTO according to the paper which is suggested. Originally it was just decreasing to 8 and adding RTT variance. Now this formula is according to the paper, so this is done. Let's get to tcp.c. So here we have made changes to retransmission. We have commented this out here, and here we have basically the initial window clamp. It was set to 0. We have set it to initial congestion window size, which we just set from 10 to 1000. Here we have set the congestion window to initial congestion window. So we are back to the original. This is basically reducing the timeout. Not reducing, increasing it by twice. We are not increasing it by twice. We are letting it as it is. TCP congestion. Okay, so this is the Reno threshold. Originally it was being decreased by half. We keep it the same. TCP congestion window, we do not make any changes, unlike the original code. That is it. We also changed TCP hybla, but it is not giving us results, so we'll skip that. So this is where we changed the receive threshold. It was initially minimum of the receive threshold and window clamp. We set it just the window clamp. Here TCP clamp window, original it was minimum of the minimum allocation, and this rmem2, which is basically the amount of memory the system can offer, so we just set it according to that. Here also, instead of selecting minimum of TCP window and this TCP advertised MSS, we just set it to window clamp. This is initial window. Originally it was set to minimum of these three values: congestion window, the 32-bit maximum integer, and the window clamp, congestion window clamp. We set it simply to congestion window clamp. Here also similarly we take the congestion window to the window clamp, not the flight packets and flight. So basically we are keeping throughout the code, we are trying to keep the window clamp as high as possible, not the window clamp, the congestion window as high as possible, which is window clamp. This was one I thought might need change, but we didn't change it. So here it is quick acknowledgements. Instead of setting it quick acts, we set it to max quick acts. Here also we set the send buffer to the available window memory according to the system, not the minimum of send memory, the current value and what is available from the system. Here we are not decreasing window, we are keeping it as much as the receive threshold. Similarly here we are not increasing it, we are just setting it directly to the window clamp. So we're done with this. This is mini socks. In here we make some changes. So here we have added two lines, new TP, basically we send the set the congestion window according to the clamp and remove these lines. That is it in mini socks and TCP output. So here we set the th window, the maximum possible 64 kilobytes instead of the receive window, and the minimum of receive window and 64 kilobytes. Here we do not select the restart congestion window as minimum of congestion window and restart, we just let it be what it is. Here we are having the congestion window. In our code we just let it be what it is. Here we are setting it to maximum of congestion window and restart congestion window, but in our original our code we are setting the congestion window to equal to the congestion window clamp. Here also we are setting the space for the initial window equal to the window clamp, a maximum of window clamp and space, not the minimum. Yes, so receive window we are setting to the max TCP window, not the minimum of space and max TCP window. Basically increasing the congestion size of the window. Similarly here, receive window, maximum of TCP window. Similarly here, here. Both places new window sizes are setting to the maximum possible. This might need change, but we haven't changed it. Here MSS, we are setting it to what it is. We are not choosing the minimum of these value, MSS now, and limit we are not setting to minimum of send window, congestion window, we are just setting it to congestion window, send window, TCP timer. So here is the model timeout. This is the most important part of the paper and our experiment. The original here halves the timeout, but here we have kept it constant 2.1 into our TO base. And if there is the linear backoff, and if it has gone exponential, we keep it the same, we do not change the timeout. Here timeout always remains the same, it always returns 0. And here is our final algorithm that we use, TCP Wino. Here we are setting the congestion window to congestion window plus 3, not plus 1 as in the original algorithm, to fasten up the increase of congestion window size. Here also we are setting the Wino threshold to the congestion window clamp, and we are not reducing it. In case of packet drop, usually it is reduced to 80% of the current value of the congestion window. We just keep it the congestion window if it is a non-congestion state. If it is in congestion state, we select the maximum of congestion, half of the congestion window, or 2, basically half of congestion window. But in congestion state, we keep it as it is. This was the code. We uploaded it to our virtual machine, and let's check. So we can see we have lab3 TCP. Let's okay, so we can see these are our files, and we have a few shell scripts, utility shell script written for our convenience. Let's go through them. For example, place.sh is basically, it places this mlab3 TCP files what we have modified into our original TCP stack. If I execute that, so let me just place it once. All files copied successfully. Then we have dot rebuild, it reboots the PC. Let's just see what rebuild sh does. This is basically the shell script. It sets the kernel source directory, TCP directory, net IPv4. Then it compiles using make command only the IPv4 section, the directory, installs the modules and reboots. So let me just reboot and then we'll set the rates and demonstrate the improved TCP performance, which is the sh. See, reboot. These are warnings for comments and side comments. It is not very it doesn't do any harm, and as we can see, it will take quite a bit time. Meanwhile, we can repeat the same procedure in the client. I think we have the client open. Also, we have the router open. We can these are the set interfaces, IP route. Now we can see qdisk show. Like we can see, these are preset. These are preset because I haven't restarted it. So see, let me just reboot the client. Is it the client? No, it's S15. We don't want to connect to that. It is rebooting. Should do the same for our client. Connect. Oh, it is open somewhere. Somewhere. Okay, so here's the client. We can also give a command rebuild.sh. So at the end we will see, not at the end, we will see a reboot command. This is S15. Close the socket. We can see here at the end we'll see a reboot signal. And let me just restart the router also and show the commands again. Just stop the instance. That's not all. I just need to stop. Basically restart the router so I can reset the commands and demonstrate. Reboot instance. Here server, it is installing the lib modules dependencies, and it will reboot in some time. It is still installing. So I'll just pause the video for a while, or rather I could just make a connection here, connect to the server. Login Ubuntu. I don't know why is it not logging, but I'll just connect through. Yes, sudo password. Ubuntu stays unchanged, but anyhow. So sudo tc qdisk show dev ens6. This is the client. Like we see, nothing, no rate is set. For the client, for the server subnet, now for the client subnet, nothing is set. So we just set the required rate and delay. Control C. We are taking 1 ms. We have the option of taking 1 microsecond also, but for better performance we are taking 1 millisecond ENS6 QC, and then ENS7. Now ENS6, ENS7. Now we can see the set rates: 100 megabit per second, 901550 burst, 1 microsecond latency. This latency is in the buffer, not the delay. 100 milliseconds delay and lost 20%. By now we should have the client up and running. Yes, we have the server up and running. Ubuntu. Yes. So here also we have a shell script to set the rates quickly. 1ms.sh rate set 1ms.sh. This is the shell script to set the rates on the server or the client. First it selects the network interface, which is ENS6. It deletes the current set configuration and this gives this command: sudo qdisk replace 100 megabits 90155 burst and latency 1 millisecond. Quit. We just apply it. 1 millisecond. So 100 megabits burst and 1 millisecond latency. We also need to set the Windows, the core kernel buffers, basically windows to a high value. Let's just select them equal to the burst core.rmm. Seems like command is something wrong. We need to give this command to set it vno. Where's vno? Yes. rmmax. In default, we also set it to burst value. We have a data.bin. Let's just check the stat data.bin file. It's exactly 1 gigabytes. Let's check the md5 sum data.bin. Sometimes it gets stuck. This is the router. By now we should have the router. This is yeah, this is the client. We set the rate in the client .sh. Set the rate. We set the default Windows size according to the burst, and else as well as the max size, we keep it equal. Okay, so we need to set the vno command. Okay, so currently it's cubic. We just set it vno. So it's vno. Let's just see if we have a data file. We have a data.bin. Stat data.bin. This is some previously received file. We just remove it. Data.bin. So now we do not see data.bin. Let's see. Okay, so here's the MD5 sum. We can later check it. So now we start our transfer. Before that, we just check the router delay. It's 100 millisecond, 20% loss, 100 megabits rate. Let's see the server side also. Same 100 megabit rate, burst 90155, delay of 100 millisecond, 20% loss, 1 millisecond latency. Let's just check once the setting of client and server rates. 600 megabits, 9015550, 1 millisecond. 100 megabits burst 90155 1. So now we will start the transfer. SCP data.pin. We're doing it from the server to the client. 10.0.1.177 home Ubuntu directory SCP pin. Okay, so now we start the transfer and here it goes. As you can see, it will take some time initially to build up the rate. Initially it's a little fast but slows down. Eventually it will convert something between 400 kilobytes to 600 kilobytes per second, somewhere in between that. So let's just see what is the size. What is this? Take some time. So initially it takes some time to build up the throughput. See, 16.6 MB. So we can see it has stabilized to certain value. It doesn't stay at that rate. It sometimes goes up, sometimes goes down. Finally, we'll have to see what the final value is. Let's just check what is the current size of the file in the client. It's 46 MB for now. Initially it stays a bit high, later it goes down. As we can see, it has decreased to certain value. sometimes even goes to as less as 450, even 350. Sometimes goes as high up as 1.7 MB, but broadly final throughput comes out to be somewhere between 400 to 600 kbps. That is kilobytes per second, somewhere 4 to 5 mbps. Sometimes it gets tall like it has right now, but on the whole it's 115 MB, 119 MB, 120, 21, 21 has stalled, again changed, stalled sometimes. Stalled for now, but it will pick up, I'm sure. Sometimes the window size matters, and I've seen the best results at 64 KB, so let me just put 64 KB. Close this. '64 65536. There, rm data dot bin. .536. So as there is no data.bin, now restart the transfer. So right now it is picking up relatively faster than previous. So as we can see, depending upon the core receive and send window size, the throughput changes. So initially the throughput's a bit high, later it goes a little down, but in the end it stays, like I said, between 400 kilobytes to 600 kilobytes. It's because of the congestion that happens because of the drop rate. Like right now it's dropping and again increasing. It keeps on happening. So basically after a while I will pause the video and resume just before it is about to finish, and to shorten the time of the video, but for now we just see what happens. I'll resume it sometime later, 3 or 4 minutes later. The rate's a bit high right now. That doesn't stay that way. So I see again the rate has dropped a bit. Right now the rate's real low, but it picks up later. It's going up right now. So roughly 26% of the file, 27% of the file has been sent. Seems like it's tall, but it won't stay that way. It's 28 to 89 bytes, 93 to 98, 300 bytes, and 1, 3. It's real high right now. Sorry. So at this moment, I'll pause the video and resume just when the file is about to be finished to be sent. Right now it's 1 Mbps, but like we saw, it doesn't stay that way. Sometimes it goes low, sometimes it's up, and finally we'll have the final throughput once the entire file is sent. It should be somewhere around 400 to 600 kilobytes per second, which is roughly 4 to 5 megabits per second, a little less than half the lab requirement, but most probably to our best ability we tried to increase it, but we couldn't do it. We suspect that it is uh, some configuration related to AWS EC2 instances. So that is our best performance for this lab. So right now I will pause this video and resume just when it is about to be finished sending. So welcome back. We can see around 97% of the file has been sent. The throughput has been varying, but somewhere around 500 kbps. Right now it's a bit high, but the final throughput will be less. So we can see it is 613.2 kilobytes per second. That is roughly, calculator, 613.2 into 8. It's around 4.9 Mbps. So like we claimed, 600 kbps, 613 kilobytes per second, roughly 4.8, 4.9 megabits per second. So it's not as per the lab requirement, it's roughly half of that, but like we said, maybe it's an AWS issue, but still it's order of magnitude better than the unmodified, which is roughly 30 kilobytes per second, 30 kilobits per second, because that was megabits per second. But anyways, this is our final performance for TCP module modification, and thank you. Part 2 and part 4, they are present in the report, but they are pretty straightforward, so we will not be demonstrating that, but we could that's pretty straightforward. We can demonstrate it anytime, but for this video we are done. Thank you so much. I forgot one thing. The MD5, although it's SCP, so it should match, but MD5 some data dot pin. That's 9BF79. Let me just see stat. It's exactly 1 gigabits and MD5 some data dot pin. 9BF79. 9BF79, so it matches. So with this we conclude part 3 of our TCP module modification, the main part. Thank you so much.